Well, hello. Welcome to our fourth week of online cosmology. And we're going to actually sort of switch out now of looking at our sort of models of the universe and start talking about actual observations of the universe. So rather than being a lecture which is going to talk about models and functional forms and so forth, we're going to take a step back now and look at the observations. And those observations are important because, of course, the observations both provide a route to actually building your model in the first place, but then having built your model, you need that model to make predictions in order that you can actually test it. So the observations are actually the key, of course, to understanding cosmology, and we've left them behind for a couple of lectures whilst we built the sort of backbone that we want to understand, and now we're going to move on. So cosmology in week 4 is about observations. The universe we live in. And in a sense, we're going to ask two questions. Today, we're going to ask, what is the total density of the universe? And of course, in what components? And the second question we're going to ask is, how does the scale factor evolve with cosmic time? And what you should know when you look at this, if you think back to the last lecture, is how interlinked these two questions are. Because if I know right now what all the different components of density in the universe are, matter, radiation, cosmological constant, etc., I can put that into the Friedmann equation, which is, okay, difficult to solve with all of those things in, but I can still put all of it in, I can solve it, and I can tell you how the scale factor evolves with cosmic time. On the other hand, if I measure how the scale factor evolves with cosmic time, I should be able to get from that what the components of the universe are. And so these are very interlinked questions, but you can also address them in different ways. So you don't only measure the total density from the scale factor, but you can measure the scale factor directly by measuring distances and redshifts to objects. So, they're challenging observations, but they're what we need to try and do today. And so the first thing we're going to do is we're just going to look at the total density and remind you that we have a critical density. This comes from setting the curvature equal to 0 in the Friedmann equation. And that critical density is given by 3h squared over 8 pi g. And of course, there's also a critical energy density, an E crit, if you like, and that's given by 3c squared h squared over 8 pi g. And these also have real values. So if I put these in the current epoch, i.e. I put some subscript zeros on here, I want to measure them in the local universe. This energy density that I have here is 1.4 times 10 to the 11 solar masses per cubic megaparsec. And this energy density is 8.3 times 10 to the minus 10 joules per cubic meter. Now these numbers look huge, right? 10 to the 11, 100 billion solar masses per cubic megaparsec. But let me just turn that around and put this into a perhaps more familiar number, kilograms per meter cubed, my SI, 9.2 times 10 to the minus 27 kilograms per cubic meter. In other words, the critical density is a few protons per cubic meter. Now, that sounds like it's very low. It sounds like we should easily exceed it, because even the very best vacuum that you can make on Earth vastly exceeds the critical density. So it should be straightforward to get there. And the first thing we therefore need to do is just add up all the different components of the universe and see what the critical density is. So the first task for us to do is to add up the density, and this is now energy density, in all the things you can think of. So in mass, in radiation, in cosmological constant, and that will give us our total energy density. And for simplicity, we're going to express this in units of the critical density. And we're going to express this as omega, which is equal to rho universe over rho cred. Or equally, E universe over E cred. And of course, we can also split this into components. So we can have omega m, omega r, omega lambda, omega total, and if omega doesn't equal 1, you can also have omega k, which is the curvature. So that's what we're going to go and do now.